Okay, so welcome to this video. If you probably get to this video is because you already have some knowledge about vibration. And here, basically, this is some of my notes. And I used to use all the time MATLAB, but recently I started to move all the codes into Python just because it's an open source. So basically, this is here the typical single degree of freedom where we have the mass, the damper, and the spring. And some initial condition, 5, initial displacement, 5, initial velocity, 1. And we need to determine the solution, okay? So this gives you how to derive very quickly the equation of motion. Anyway, in this case, we know we'll be critically damped with a damping ratio of 0.118. The analytical solution will be under this form. And if this is Runge-Kutta, I'm not going to go in detail. This is a MATLAB code. But basically, this is the form of the solution. So what I'm going to do is move like all this code over here, if you want, into Python, okay? So let's do that. So without wasting any time, I know you might not be interested in all this stuff. Here we go. All right, so this is Python. So basically, this is, I've opened the libraries. I do it a bit different than other people. It's because I'm really used to MATLAB, so I don't want to use the for NP in front of every single command. So basically I do imports from everything. So from NumPy, I'm going to import the commands arrange, square root, exponential, cosine, sine. From NumPy, lin, algebra, I import the inverse. And from the matplotlib, I'm going to import pyplot as PLT. And I could almost, yes. So basically this is the variables of the program. M equal to 100, K equal 1000, and damping equal to 100. So basically, same data as we have over here. All right. And later on, you see the initial conditions over here, set a displacement of 5. And this is, this is just to define the natural frequency. And this is the psi, which should be the value of 0.118. And this is the critical damping, okay, that you can calculate. Here, I use Spider, so every time you want to see something, you need to print it. In this case, I mean, I can activate to print it if you want, so you can see it. But otherwise, it's not activated here, so I activate it. All right. So now, what's interesting is how to get the numerical solution. So for that, let us go back to a document over here. Okay. So this is a time-stepping solution. This is our single degree of freedom. And once we're done with the single degree of freedom, I can expand this to a multi-degree of freedom with no problem at all, okay? So this is our single degree of freedom, more general with the forcing force on the right-hand side. And the trick over here, when you solve a numerical solution, is always to rewrite it on the state space form or representation. So in order to do that, in this case, I use y bar equal to x dot. So first derivative x and y bar dot equal to x double dot x. Okay. If you look at the notes over here in MATLAB, instead of having to use the dot, I like to use the z and x, but it's the same thing. Okay, same procedure. Don't get confused because of that. All right. So let me go back to this. So basically, I can write this equation here where you see that the x double dot x is really y dot, and this is really y, okay? But I can write it under this form. You see you have what? M times x double dot, all right? Then would be plus c x dot equal f of t. But now, what happened over here? We'll have 1x dot minus 1x dot. So this will eliminate, so that we get this equation. I always get this question, but yes, we could also rewrite under this form. We will have here mx double dot plus c x dot, okay, minus 1x. All we need to do is to eliminate this one. So 1x minus 1x dot plus kx equal to f of t. So now you can define a as being equal to this or this, and b as being equal to this or this. In this case, I'm going to use the top one. Okay, so this would be my matrix A, and this would be my matrix B. So we can rewrite this equation here under this form and recalling that this expression at this y dot y equal f of t. Now using vector algebra or matrices algebra, basically, you need to do the inverse and be careful because the order is important when you do matrix manipulation. So the y dot, which is really is over here defined as the x double dot x, is equal to the inverse of matrix A dot product of the force minus by. So the explicit solution, which is the discretization of the time-stepping solution, an approximation for the derivative is always of the form time step up minus 1 step divided by the interval. So this is the approximation of y dot. In this case, should be equal to the inverse of A f minus by of t. So over here, we solve now for y of t, which would be the future step. We have this equation. So this is basically the explicit solution, which is called the time-stepping solution. In this case, generally is not used for a structural problem, but it's really used a lot in the heat transfer of fluids, okay? And so in order to start the numerical solution, we need some initial conditions that we know in our case are just initial displacement 5, initial velocity 1, okay? I go to spider, this was given over here, okay? So over here, what's important to see is that, so if you want to look at the code, here I define the time step, which is really important. And I create here, the time step is going to be between 0 and 20 seconds. This is enough time for the solution to converge. And all these cases here really, I mean, I just want to do this problem in general. So if the damping is equal to 1, we know it's critically damp. So this will be the exact solution will be given by these equations here. If the damping is higher than 1, it will be over damped. This will be the solution. If it's lower than 1, it will be under damped. This will be the exact solution, okay? So this is just, I just did data trade to check the length, because once you plot, you want the length of these two vectors to be the same. And here now I define the matrix A that we defined before as M0, 0, 1. So basically here, what I am defining is, oops, these matrices over here, A and B, okay? M0, M01, and B. That you can see over here, print A, print B, you can eliminate that. And this is the force vector, which in our case, which should be 0. Okay, F equal to 0 over here. But you can put a value. So now, for time step, this is for the time stepping, we're going to append the values of y1 and the y0. So what are these ones over here? Really here, what we are appending are the values of x dot and x, okay? So the first one is the velocity, the second one is the displacement. So the first one is the velocity. The first one is the velocity, the second one is the displacement. Remember that in Python, the index starts at 0, not at 1, okay? All right, so it should be the first one, and this is the second one. And all right, so this is the figures. And this is the solution to time stepping. So from time step, from 0 to 20, another force in this case, this would be for forcing function, the cosine form, but in our case, this is 0, so don't worry about it. Y of t equal y plus dt of the inverse of A, the dot product of f minus b dot of y. So basically, that's over here, what we are doing over here. And look at this term, because this term is very important, okay? All right, so I'm sure that in the video you have plenty of time just to copy the code. Then this is just to do figure. Here I'm just going to do 3 figures. One, upload the analytical solution. I could almost skip this one, okay? In this one, upload the numerical solution, and here upload both of them. together. So if you want, you could almost eliminate these ones over here, plot 1 and 2, and just keep the last one. So if I run this code, I use Spider. So it's running. So this should be just the analytical solution in dots. So you see, after a certain time, it's going to converge. And this is the phase plot representation where you have displacement in function of velocity. So you see that you start over here, and as the time goes, it damps all the way down. So this is what's giving you the analytical solution. This is what we get with the numerical solution. You say they're almost identical. And this is the combined one, the one on top of each other. All right. So here I'm deleting not to have too many figures, but what is really important here is the time step. Because explicit solution is good, but the bad thing about time stepping solution, or in general explicit solution, is that they need very small integrations time. So the dt will be very small. So let's see what happens if we use dt of 0.1. So again, you see, this will be the analytical solution. But now you see that this one is like if it was no damping at all. All right, it just stays on top and we'll get one circle. So this is exactly like if it was no damping. So we don't get a solution, and we compare, you see, you will get the wrong solution. All right, so that would not work. Let's see what happens if we get 0.01. And if we run it, so again, this is the analytical solution. And now this is the time stepping solution, the explicit solution. So now we can see the damping. And you see here that we get a pretty good solution, but it's still not identical. All right, but it's reasonably good. Now, when we move to 0.001, which is the one we had initially, now is when we get they're basically identical, okay? Both solutions. All right, something I might do another video, but here I just wanted to show you very quick, is that if I solve the same problem with the rule ejecuta, which basically means that if you see here this function here, the inverse of a f minus d dot, so basically this function here, instead of doing the time stepping solution over here, we use with rule ejecuta, which basically means you use rule ejecuta to solve this term, okay? And without going into many details, I might do a video, we'll see. But basically, if you are familiar a little bit with numerical solution, if you look at the code here, it's basically identical. All this part is completely identical, except this is identical again for A and B, except that here, I need to do the rule ejecuta. So rule ejecuta basically uses a function g. I create a function g to solve this part over here, okay? And basically you see is 1/2. You can go into detail. And this is the only thing that changes, is that I just go through the procedure, and when I need to solve for this, I just call this function over here. All right. So you will see this. So you see here, I do the same thing. Y equal y dot plus rule ejecuta of y times dt. Here I had y equal y times dt times all this stuff. Now I do exactly the same thing over here, but I use the rule ejecuta to solve for that term. But basically the rest is identical. Let's see what I have here. Plotting together. Here I save some time, I just plot them together. But here what's important is that you see here with the time step of 0.1, all right? And if I run this, we get right away the exact solution. So for the time stepping, we needed to use 0.001, okay, in order to get a good solution. With rule ejecuta, only by using 0.1, we get the exact solution. Basically, this is an implicit solution. And without getting into too many details, the advantage of the explicit solution is that once they start converging, they're always going to give you the right answer. Otherwise, generally they will diverge and tell you that they cannot find an answer. So the good thing about this the implicit solution, which I guess that's the way I call it. Let's see. Together, the implicit solution is that once it gives you a solution, generally it gives you the appropriate one, which is not the same thing with the time stepping or the explicit solution, which always gives you a solution, but that doesn't mean is the correct one. Again, I will put all this information here. I haven't done it yet, but probably okay, Johnny, I put it on this website. Here I have a fee map here tab with a lot of videos. You might be interested or not. I will probably create another one here with Python where I will start putting these videos, and you see probably you have access to the other files. All right, so I hope you liked this. I might do one specific video for this one so I get more details if you're interested. But this is basically what's important, okay? That you see the difference between the explicit and implicit solutions. So I hope this video was helpful and that you can use this code for some of your classes or for whatever you need them. Thank you for your time.